Hello, this is the 18th video of our linear algebra series. Today we will have polar decomposition and singular value decomposition. Last time we have isometries and positive operators, and then we provide some characterization of these operators. Today we will explore on the first polar decomposition, and then we will relate isometries and positive operator. We will use the concept of isometries and positive operators here. Let's begin with polar decomposition. So polar decomposition. First, let's have the analogy between C and the vector space LV. So in this analogy, is a complex number. We have this complex number Z, and corresponding to this, we have the operator T. And then if we have the conjugate of our complex number, then we have the adjoint of our T. And then the real numbers are those sub-adjoint. So if your Z is equal to Z bar, so these are real numbers, then this correspond to sub-adjoint operators T, so that T here is just equal to the adjoint. And then the non-negative numbers, of course, are the non-negative operators, or I mean in this context, so non-negative numbers, we correspond these to positive operators. And what? A subset of C is the unit circle, which consists of complex numbers Z, such that Z, the absolute value of Z is equal to 1. This is Z is equal to 1. Under this the correspondence, we have here T star is equal to I. Okay, let me replace this bar at the first one, so it would be T star is T is equal to I. So here, this is T is an isometry. So the unit circle here correspond to isometry. Now we will continue our analogy to the following notion. If we have non-zero, if we have the non-zero complex number, we can express Z here as this times this Z. And we know that this C, we can write this as square root of Z. So this part here is element of unit circle. So this correspond to isometries. And then this part here is positive square root. So this is positive. So here, our goal is express the linear operator as isometry times this part. Okay, let me this is isometry, and then this is the usual positive operator that we have. Okay, let us define some notions first. Let's define our square root of this. T is a positive operator. And the square root of t is unique positive square root of t. Note that in here, t star t is positive for every t in the here, and then the square root of t stars t is well defined because satisfies our definition here. And now we are ready to prove or to state our main theorem for this section, the polar decomposition. Which is called the polar decomposition. T linear operator. Then there exists an isometry S such that, of course, this is also a linear operator. Your T is expressed as S times this square root of T adjoint times T. All right, let's continue. Here, we will prove this. This is relatively a long proof, but bear with me. Some of the proof are left for exercise, and they are easy to show. Let us first start with a vector in our vector space. And then we take the magnitude of that. This is just this. Because t is here, we can express it as and also this can be written as t star t and then multiplied by itself twice, the square root v and v. Now, because it's positive, we can just do this. And thus this is equal to the norm of as we get our TV is for all V. We have the same norm. So now define a linear map S1 from the range of to the range of T. And then if you have V here, you get it mapped to just T of V. Okay, so we have the idea is to extend S1 to an isometry, not just in the range, but of the whole LV, such that your T will be S E star T square root. This is what we want to show. Okay, let's show this very detailed, very explicitly. So you want to show first that S1 is well defined. Indeed, if we get V1 and V2 in the space such that your V star T of V1 is equal to V2. We want to show here that T of V1 is just equal to T of V2. And then here, T of V1 minus T V2 is just equal to T of V1 minus V2. Here we get since the norm we have shown earlier that this norm is of T and T square root of are the same, we can express it here as V2. This is before from above. Okay, let's I'm doing it slowly because it's like then T star T of V1 minus T star square root of T star T of V2 norm. So we know from our assumption that this is true and we get 0. This means that our TV1 is just equal to TV2 as desired, and S1 is well defined. Well defined, and then I will claim here that the S1 is linear map. And then the proof or the verification is verification is left to the reader. And then upon showing that this is a linear map, so claiming this is a linear map, we will see that S1 maps the range of the square root of t star t onto the range of t. So here, S1 sends the range of the square root onto the range of t. So from above, from our this part here and this part, we will this will imply that S, the magnitude of U, is equal to U here for all the U in the range of the square root of T star T. In particular, S1 is injective. Thus, we have the dimension of a range is equal to the dimension of the range of T by the fundamental theorem of our linear maps. So using our fact on the orthogonal complement, this will also imply that the dimension of the range of complement is equal to the dimension of the range T complement. Thus we have an orthonormal basis can be chosen. So we can choose E1, En, F1, Fn. Orthonormal basis, they are two distinct two of same length. Let us say the length is m. So now we want to define another linear map, S2, which map the range of square root of T star T complement to the range of T complement, and then S2 of sum I from 1 to n is just sum I from 1 to n. So here, for all the W in the range of square root of the complement, we have S2 W is just W by 6.25, which is on inner product. 26.25 here says that If we have an orthonormal basis, then it's just the norm of the combination is just something like the norm of each component. You can check that on theorem 6.25. And going back, where are we? So define an operator S on V. So let S be an operator on V such that if you restrict S on the range of this is S in okay. Hello, hello. I think my screen here stopped. Let me share again. Okay, my screen stopped. Let me. Okay, here it is. I think this is now available. Define S1 S to be S1, and then this is equal to S2 on the range of the orthogonal complement of this. Okay. Now, if we have a vector V in the vector space, can write V is equal to U plus W, where here U and W are element of the first one is this, and here this is just on the complement. And of course, we know that they are disjoint. So if you apply S to V, can just have it S of U plus S2 of W. Okay. Now for each V, S of V is equal to S1 of square root of T star T V. This is just T of V. So your T here is equal to S. Then root of T as desired. Okay. All right. So we are now left to show that S is isometry. This is easy. So we will just use Pythagorean theorem. Here, S of V squared is just S1 U plus S2 of W squared. And because they are disjoint, we can write this as S1 of U squared plus S2 of W squared. And because they are isometry, we have just U squared plus W squared, and this is just equal to V squared by Pythagorean isometry, Pythagorean theorem. And this ends our proof. I have a connection problem. I think I'll pause a little bit after this one, after polar decomposition. Okay, now let me have some remarks before I end. Okay, have connection problems. Here, your polar decomposition uh, express a linear operator T in V as a sum isometry times this. And this is an isometry. This is positive operator, or in the right term, non-negative operator. And we know we have characterized them from the previous meeting, or video or discussion. So we can write a linear operator as product of two operators, namely the isometry and positive operator. And these two types of operator are already completely described in the previous meeting. So isometries and positive operators. Now, for if your field is the complex numbers, and suppose your T is just this is polar decomposition of our operator T and S isometry. Then there is an orthonormal basis of V with respect to which S has diagonal matrix. And there is also an orthonormal basis of V with respect to which this one has a diagonal matrix. Okay, so let me put a warning here. that there may not exist an orthonormal basis that puts the matrices of both S and T these into nice diagonal forms. So in other words, S may require S may and T here, this T star T may require different orthonormal basis so that they will be expressed into diagonal matrices. So I think I'll end here because of connection problems. So I'll go back. I'll record another one for singular value decomposition.